you'd see that one of the critical steps is validation, or more general, model verification and model validation, which, narrowly speaking, comes after the formal model is complete and before you start simulation analysis, simulation experiments and policy design. So technically speaking, if you remember the methodology, right after the model is complete, before you start your simulation experiments, analysis, design, so forth, you need to do a formal model verification and model validation. Now, but that's only, as I said, narrowly and technically speaking, because as we discussed briefly, really model validity testing is a prolonged process spread throughout the methodology. So really, model validity testing starts from the day you start constructing the model to the day you are doing your final policy analysis, policy improvement, conclusion, derivation, so forth. So it's a distributed process. There is really, philosophically speaking, not a clear-cut, isolated step of model validity testing and verification. On the other hand, in general, we do talk about a sort of sixth step called model verification and model validation, just because most of the formal act of validity testing takes place in that stage right after formal model is complete and before you start your formal analysis. Now, okay, so then this series of slides is a discussion of some concepts and tools, methods and tools on what we call model validity testing. What model validity is and what model validity testing is about. Some of these things you already know from IE 550. So it's just a more extended discussion of sorts of things you already know from IE 550. But some of these are new. All right, now, so when we talk about model validity, model validation testing, the first thing is some conceptual foundations. As you recall again, most of these things you need to recall from IE 550. First of all, when you even start talking about model validity, the notion of model validity, there is a big, major difference between validity of statistical forecasting models, black box models, and validity of system dynamics-like models, causal descriptive models, causal models, or what you can call transparent models, theory-like models. They are like scientific theories. They claim to explain the world. They claim to provide a causal summary, approximate, yet causal description of some real processes. So in that sense, they are very different. Well, again, as you recall, we discussed these things earlier. We should know these things. As you recall, the fundamental difference is a short-term forecasting model, a correlational, non-causal short-term forecasting model is valid if it provides a accurate enough short-term forecast prediction. That's it. So the validity is measured by its ability to provide accurate enough short-term forecast. All right. So it sort of looks like this. There is some data points like this, and then you fit a regression line, let us say, a non-causal equation, right? And then you predict the future. You say the future is the prediction. This is your prediction with your model. Let us say it's like a 2.3 point forecast, like weather forecasting or price forecasting, demand forecasting. So you do that, and then after this, you observe the real outcome, real observations. And let us say real observations are here. As an example. Well, one of them is here, one of them was here. And then, well, let us say you had one more, so 3 points. So you do this, and then the third one was here. So, well, perhaps your forecasts are not perhaps that great, right? There we have some consistent errors there. Forecast errors are not small enough. So what do you do then? The next time around, before you do forecasting, you remember you revise your what? The parameters of your regression model. So now, having observed this, your new model looks like this, something like this, perhaps, right? Okay? And then you write it. Actually, or you may write it to whole, or you may write it, you do something like this. It depends on the techniques you use. But anyway, now you have a new forecasting model. And then you do again. Now this one perhaps will provide these 3 points, right? And then you will again observe 3 points, and now perhaps they are like this, the three real data points. And now you like this, perhaps you don't touch much, and then you say my new model is this and my forecast is this. So this is how the game is played. Each time you obtain, you generate a 2, 3, 4 point ahead forecast, and then you observe real data, and then you do it again. Each time you see that the forecast errors are not good enough, you revise and you modify your model. So this has a name too. This is this type of correlational short-term forecasting models. Sometimes they have a name there. They're called ex-post predictions. This is ex-post forecasting, ex-post prediction. You know, ex-post means after the fact, right? Or post-war, right? Ex-post. So it means that you do, every time you do a forecast, you do it after having observed and revised your model based on new information. Okay? And there's a good reason why. And these models don't have to claim, they don't need to claim, they don't claim any causality, any causal descriptive power. So that if I write an equation here, this is let us say this is demand forecast for automobile tire sales, and the equation may very well look like something like this. The demand forecast for automobile tire sales, call it Y. Y of T equals square root of bank balances, right? Plus logarithm of milk consumption, and plus, you know, some function of time, right? I don't know, you know, some power of t to do something, some function of time, or something else. When you look at the equation, so you have this milk consumption and bank balances, they don't causally what? Produce tire sales. There is no causal link there. All right? So the model doesn't claim any causal structure, any causal meaning. So in that sense, the validity is only judged by what? By the predictive power, the short-term forecast power, the short-term predictive power. That's how we judge it. That's it. So in this sense, it's philosophically non-problematic. There is a complete, easy agreement on what? On what constitutes validity. It is basically, in this kind of extreme forecasting model, if it provides a good enough this prediction, it's valid. If it doesn't, then it's not valid enough. And then how you do it is not very problematic either, very deep. Well, it can be complicated, but it's not philosophically problematic. How you assess it is by a series of statistical measures, right? The statistical estimate measures of what? Of the errors between forecasts and real observations. Of course, there are all sorts of statistical issues there. You know, the collinearity, the collinearity relationships between independent variables, normality assumption, independence assumption, and normality of the errors, and all sorts of homogeneity of data, all sorts of statistical issues. But those are statistical difficulties, have nothing to do with the structural meaning validity of the given equation. All right. So it's a purely, more or less, statistical numerical task. Well, when you go to descriptive policy models, theory-like models, causal descriptive models, where system dynamics models belong, there you suddenly have two very different aspects of validity. One is something like this, which is still quite different, behavior or output validity, which is basically all there is to validity in ex post forecast models. But in system dynamics models, only one component is what is behavior validity, output validity. The other major, more important component is structural validity, which is the logical causal acceptability, justifiability of the structure of the model. That is, do the relations in the model reasonably correspond or reasonably approximate the real relations that exist in the real system with respect to the problem I'm interested in. So we say a system dynamics model is said to be valid. First, it has a acceptable structure, an acceptable, reasonable representation of the real structure, and then two, only then, secondly, if it can further reproduce the dynamical behavior patterns that exist in the real system. So, structural validity and behavior validity. So these notions you already know from IE. Now, in short, we sometimes say a system dynamics model is valid if it produces the right behaviors for the right reason. The right behaviors, the term right is of course philosophically wrong there. Right is philosophically wrong. So that term right is, there's no such thing as right behavior, of course. It should be valid or reasonable behaviors. But anyway, so the motto is, right behaviors for the right reasons. It's a nice slogan, cliche. Right behaviors for the right reasons. Not only the right behaviors, but also for the right reasons, by virtue of having valid structures. All right. Now, as soon as you say that, you realize that system dynamics models are in the domain of philosophy of science. Now we are playing a game which is in the domain, now we're in the field of what? Science, so to speak. You see, science, natural sciences, classical sciences, have had this debate of validity or verification, sometimes called verification in science, sometimes called justification, theory justification, or knowledge justification, epistemology, philosophy of science. They've been discussing this for centuries. Now, because it's a difficult problem. Now, the problem is difficult because it's not a simple statistical measurement, quantitative measurement question. It's a logical act, okay? You are trying to convince people, your community, that you are coming up, you are suggesting, proposing this model structure, this set of relationships that are for sure an extreme simplification of the reality, but yet an acceptable simplification of reality. Just like a good cartoon, okay? A good caricature or a good cartoon of a person. I always give this example. If you take a look at this famous good cartoon of Charlie Chaplin. You know that this classical. You know that this is like 5 lines. Or Alfred Hitchcock. You know, Alfred Hitchcock has a famous there's a famous drawing of Alfred Hitchcock. You know, there's this guy, fat guy, and there's there's a cigar, and then there's a silhouette of him. And if you know Alfred Hitchcock or Charlie Chaplin, you can immediately recognize that that's a very valid one, simplification of Charlie Chaplin. Now, it only involves 5 lines, 5 curves, and it's Hitchcock. And the other one only involves, again, 5 lines, and it's Charlie Chaplin. Now, I can sit down here and try to give you a very nice description, drawing of Charlie Chaplin with 25 lines, and it will look terrible. And you'll immediately say what? My drawing is not at all a good characterization of Charlie Chaplin. And this goes for all the good caricatures of politicians, you know. These great cartoon drawers, artists, have this talent of drawing some person, right, or some usually a person, with only 5, 6 line strokes, right? Models are like that. Right? Models are extreme simplifications of reality, yet they look like reality. In some sense, they are very nice summaries of real problems, although they are extreme simplification. Well, you see, this act in arts, of course, you know, we kind of agree, and it's a question of taste, and it's a question of visual aesthetics and taste, all of that. But in science, we cannot quite proceed that way. We cannot say, okay, here, you know, here E equals mc squared, or F equals ma, and this is a model, simplified model of the real dynamics, you know, at high speeds or low speeds, whatever. And we say, well, it's not like cartoon of Hitchcock. You know, you cannot kind of look at it and say, this is nice. But the problem is sort of like that. You know, how do you convince people, the whole scientific community, that this oversimplification yet gives a great summary description of what? Of that complicated real problem that has zillions of variables. So here you have a few variables, reality has zillions of variables. How do you demonstrate that? That's structural validation in system dynamics. That's scientific theory justification in science. That's our whole philosophical piece of scientific theory justification. And there is a big discussion that can we prove positively, show let us say, let me just use a terminology. Can we positively prove that a scientific theory is a valid description of a real system, period? That's a big philosophical discussion. So some logical empiricists or positivists have argued for many decades that that should be possible. If you use a proper philosophical methodology and we have a good theory, we should be able to prove positive, for sure, that that is a valid model, scientific model. All right? And then we should be able to, this way, separate valid models, scientific models, from invalid scientific models, for sure. Where the more relativist or conversationist school, on the other hand, argues that there is no absolute truth, there is no absolutely valid models. All models are sort of just temporarily and accepted, conveniently accepted, as if they were true models of reality. But these are all conventions, so we can never prove philosophically that a model is a valid description of a real problem. Even if it's a simple problem, I mean, you observe something, an immediate observation, a simple and immediate observation, they argue that you can still not claim to build a valid model for sure, and you can never prove that any model will be positively and definitely a valid model of any given real system. So you just have these approximations, and you try to establish confidence, build confidence. The term that they use is building confidence. Science is an act of building confidence, establishing confidence in the validity of these theories. So if you borrow from them in system dynamics, validation and validity testing is an act of building confidence, establishing confidence gradually in the believability, in the credibility of these models. So there is no valid, invalid model. There is no true-false model. There is no right-wrong model. John Sturman had an article that started, all models are wrong. Okay, so that's true, of course, philosophically. All models are wrong. There is no such thing as a right model or wrong. The question is, which ones do you still use? Which models are less wrong than the others? Those are the ones that you adopt and use. So it's a then structural validity then indicates a spectrum, not yes or no. You don't have true or false models. You don't have right or wrong models. You don't have invalid or valid models. You have models that are just great, a spectrum. You know, you can say extremely valid, highly valid, reasonably valid, fairly valid. Then you come to my models, you know, so-so models, bad models, terrible models. Okay, so this is a spectrum. And at some point, you have a threshold where you say, oh, I'm not going to use this model, just reject it. And in that sense, different people may have different thresholds. It's subjective. A given model may be used by a group of people, but may be rejected by some other persons because of the cost involved in using that model. Type 1 error versus type 2 error, so forth. The other, so this is all philosophy of science issues. If you're curious about it, you can do a lot of reading. On that, I have an article that goes all the way to 1990. My minor was in philosophy of science, philosophy and sociology of science when I was doing a PhD. So you wrote this paper, and there's a little bit of this in 1996 and 1990. I'm trying to write right now another paper on summarizing these issues. It's slightly more up-to-date version of the 1993. All right, now, so if you continue with structural validity then, by the way, I talked about statistical significance on the previous page. The statistical significance is also a philosophically problematic term when it comes to model validity testing. For one reason is, you know, in model validity testing, test of hypothesis looks like this. H0 says what? Model is equal to reality, right? I mean, statistically speaking, right? Can be assumed to be equal to reality, right? And you are trying to reject that. H1 says, well, alternative, it's not equal to reality. Now, the problem, the statistical problem is the following. Even if you had a fantastic test, if you reject H0, as you know from statistics, it's a strong result, right? It's a strong and useful result if you are able to reject H0. If you can reject that, I'm not going to get into that. This has to do with the H0 assumes a certain state of the world, and if the outcome contradicts the state of the world assumed, then you have a strong result. You say, I'm rejecting H0 cannot be true. But if you cannot reject, then that's a what? very weak, inconclusive result. You know this from statistics. You cannot say anything about state of the world because an outcome that tells you not to reject H0 can come from any state of the world, including H0 or something that may not be H0. You know, if you do these normal curves, you can immediately understand what I'm talking about. You know. An outcome here can come from anything, but if an outcome over here, you say, there's only 5% probability that can come from here, so with 5% error, you can reject one, H0. This is the great foundation of what? Statistical custom hypothesis. Well, here's the problem. in validation, H0 says what? Model is statistically approximately can be assumed to be equal to what? Real system. And H1 says not. If you reject H0, you have a strong result that you don't like. That's not very practically useful for you. Alright? So what are you going to do next? If you fail to reject, you think you just validated the model, but you didn't. All you have is an inconclusive result. That's why statistical hypothesis testing is not strong at all in validity testing. In policy analysis, it's strong. Why? Because in policy analysis, the statement looks like this. H0 says what? Model behavior is equal to real behavior. H1 says model behavior, let us say, has a smaller amplitude than real amplitude. Now, if you reject H0, you just established what? A strong result on what? On the fact that you reduce the amplitude of the what? Of the behavior. Do you see what I mean? So by rejecting H0 in policy analysis, you can establish very strong results. So that's one of the big, you know, again, issues in why, you know, this whole notion of hypothesis testing is very problematic when it comes to validity. That's why validity is that's why it's a very complicated philosophical problem. So in policy analysis, it's great. You know, your objective is to reject H0, and if you reject H0, you have a very productive result. You just move on. But in validation, if you reject H0, you cannot move on. If you don't reject H0, you have an inconclusive result. So in either case, you stop. Or actually, you don't stop, you move on, but you know,